Hey everyone, welcome to a review video for the test on exponents, Unit 9, with a little bit of cumulative questions as well. So here are the questions I looked through that I thought would be important to go over. These are the questions that I'll be reviewing with you today. Feel free to skip to whichever ones you need, and if there's something that's driving you nuts and you can't figure it out, well then certainly you can email me. And I can pop up a video response for you, maybe tomorrow or something when I have time. But that's always an option for you if one question is completely driving you crazy, even after looking at the answer key online. I wouldn't mind giving you a response. Okay? All right, so let's go. Let's take a look at 1. Here's the rule for simplifying exponents. You want to keep them positive. And what I like to do is take care of the power rule first. So first let's do power rules. Whoa, that was my fire alarm. Again, let's do power rules first, followed by product rule, followed by division rule. So we know that power means multiply, product means add, and dividing means subtract. If you do them in that order, you'll be fine. So let's take this -1 and distribute it first. And it needs to go to everybody. This is a big briefcase that the 1 is attached to, so let's apply this everywhere. Tops, bottoms, the whole thing. Here we go. Okay, so that was the -1 being distributed. What I'm going to do over here is just to say, because I forgot, I want to do negatives last. When you're all done, worry about the negatives. Don't worry about them now. You'll see what I mean in a second. Okay, so we did the power rule. We do have some product rules I see down here with the y's in the denominator. So we need to do that. So step 2. The top won't change. It'll still be like this. However, the denominator, we will add those 4 plus -1, which is 3. So now my y's can be combined to be 3. The x has nobody, so we'll just leave it as a -3. And we have now completed the product rule. What's left is division. Now the rule for division is subtraction. So, again, leave the negatives where they are for the time being. Y is going to be y to the -1 subtract +3. The x's will be +1 subtract -3. And that's the gotcha right there. It's the double negative, so you're actually going to add. So let's simplify this. We have 2 to the -1 times y to the -4 times x to the +4. Now, when you're done, let's take care of the negatives. So over here, just for space, I'm going to send the 2 downtown and make it the exponent positive. I'm going to send the y downtown and make that exponent positive, but I'll leave the x up top because it already is positive. And this should be your final answer. Power rule first, followed by product, followed by division. Last, negatives. So let's take a look at this one with the fractions. The power rules exist down here and here. So let's go ahead and distribute to everybody. And we'll leave the top the way it is for now. So on the top I have x, y to the 1/3. Then here's where the bottom gets really juicy. Okay, so on the bottom I have 5/3 times negative 1/3. So that will be x to the negative 5/9. My y will be y to the 5/6. You remember that you multiply tops and bottoms when you do fractions. Okay, this whole thing is now multiplied by whatever happens here. So I see that I'll have x to the 2/9 and y to the negative 2/6. Cool. All right, so the power rules have been taken care of. Let's see if there's any product rules hanging out. I do see that we have some x's that are like, and we have some y's that are likes. So let's go ahead and add their exponents and see what happens. Okay. So we still have xy to the 1/3 up top. Over. Now we're going to have x to the negative 5/9 plus 2/9 times y to the 5/6 plus a negative 2/6. Okay, so let's add those. What we end up with is negative 5 plus 2 is negative 3 over 9. So on the bottom, my x's are x to the negative 3 over 9. And my y's are 5/6 minus 2/6. Well, that's 3/6. And much of this can be done in your calculator. I'm just doing it right now by hand. But please use the calculator for fractions. Okay, let's simplify. So for example, I would like to simplify these two fractions because I see they're very easy to do. So x times y to the 1/3 on top of x to the negative 1/3 y to the positive 1/2. Just makes it look nicer. Okay, so now let's do the division rule now that we've finished with products. So we're basically going to have x to the 1 minus negative 1/3. And then for my y's, I will have y to the 1/3 take away 1/2. Again, calculators. What do we get? 1 minus negative 1/3. That turns out to actually be positive 4/3. And then for the y's, using your calculator, you would get negative 1/6. Okay, so we're done with division rules. Let's take care of the negatives. We simplify this final answer to be x to the positive 4/3 on top, y to the positive 1/6 on the bottom. That's your answer. Cool. Okay, let's go to number 7. This guy. Now, something to know, this is the same as, it's just the test generator that we use. Sometimes it uses a different syntax, or structure, I should say. This is the same as saying this: 3 times the 5th root of r squared inside. So if you see something outside the radical, it's the same as it being underneath. And I just say that because I know when we taught this, we like to say that we had the in over the out exponent. So if we wanted to convert radicals to fractional exponents, we would take the in number, which is meant to be this 2 right here, and the out number, which is meant to be the number outside the radical. So I could see how if you see this, you might be confused and say, well, wait, the 2 is just as outside as the 5 is. This just happens to be the software we use sometimes to create questions, and they put the 2 on the outside of the radical. But they are equivalent. So with that in mind, this answer here would be 3 times r to the 2, which is the in, over the 5, which is the out. Very important that we didn't use parentheses around the 3r. Number 10, what's curious about this is these parentheses right here with this 5 on the outside. That tells me, the loyal exponent, right, that 5 is talking to everybody inside this briefcase. So it's the n has the 5, but so does the 2. So when we take this out to make it a fraction, that's when you have to be very careful to use parentheses around that 2n and then raise it to the 5/3. A little different than this guy, wouldn't you say? The parentheses mean everything. Okay, so that was a good one. Let's now turn to 13. Okay, so these questions here, sorry, 12 and 13, we want to do this. We want to take rational exponents, fancy way at dinner parties to talk about fractions. We want to take rational exponents and turn them into radicals. So what we do is call this the in and this the out. Cool. So in means inside the radical. Out means over here. Now who, this is really critical, who is talking to this radical? I'm sorry, this exponent. You got to remember the story about the loyal exponents. This negative 1/6 is only attached to the x because there's no parentheses. So this 7 is as good as just hanging on outside like this. 7 times. Please be careful of the parentheses, or especially when there's no parentheses. Okay, so let's do this problem. I see a negative, which means I'm going to write 7 over x to the positive 1/6. That's my first step. Let's take care of that negative. Now we know we have the in over the out, so 7 on top of radical x. The in number is a 1. The out number was a 6, and it's no longer negative, right? Because we took care of that by putting it in the basement. So this becomes a 6. That's your answer. "13 is just slightly different from 12 in that it does have parentheses. So when we make this guy positive, which we always want to do, we will send the entire thing to the denominator. And we will use parentheses, otherwise we're wrong. So we'll make that a positive 5/3. Now I think you guys know the rest because this is in over out. So we're going to say 1 over, we'll put a radical down here. The 2v has to have parentheses, otherwise the v is the only one who's going to get the 5. If you don't use parentheses, you're wrong. And then the 3 is over here. Cool. Sweet. Okay, 15. Solve each equation. The way you get rid of exponents, like take a step back for a second. I'm sorry to bore you if this is boring, but just take a step back for 1 second. If you had an equation, right? This is an equation. It's no different than this guy. But if you had an equation like this where you're trying to solve for a letter, like letter n, you want to get it alone. You want it to say n equals, right? That's what we're talking about. So something simple like this one, you would just divide by 2, and you'd get n equals 4, and you're happy. There's no difference when it comes to this equation. We want to get this n all by itself. In other words, n to the first power, all by itself. So hopefully you'll recognize this scenario, that when you're trying to get n all by itself, you're going to need to get rid of that exponent. And the way to get rid of it is to use reciprocals. And when you use the reciprocal, you're talking about the power rule. Now, to back up one more step, apologies, just the basics, right? When we did solve this before, something really important, you divide 2 here, You also divide 2 here because it's an equation. You have to keep everything fair and balanced. So when we do this reciprocal business, we want to make sure we do it to both sides. And if you know that, you're fine. So watch. We see 7/6, right? So the reciprocal of 7/6 is 6/7, because what happens when you multiply these two fractions is you get a 1. So we can go over here, and just like we divided both sides of the equation by 2 before, right? We can raise both sides of this equation by the 6/7 like this. As long as we do it to both sides, we're fine. Now the nice thing is the power rule says to multiply. So when we multiply these, it turns into a 1. And I have no idea what this is. I couldn't. But that's why we use the calculator. So in the calculator, just say 128 to the 6/7. Make sure you use parentheses. Or if you have the new fancy calculator, make sure you put the fraction up in the exponent area, and you'll get 64. And that's it. So it's important that you just recognize how to solve equations. You want to isolate a variable. Well, if that variable for some reason has an exponent attached, you can easily get rid of that exponent by raising it to the reciprocal power. I like question 18 just because it's a little bit more complicated. Not very much more, but it's complicated because we can't just go up and start raising stuff to the 5/1, because you can see that is the reciprocal, right? You got to get rid of things that are attached. There can be nothing here. You don't want anything adding or subtracting here. So we just have to do a little bit of setup first. So I wanted to do this question with you so you can see that. Okay, so nice thin line. Okay, let's get rid of this 4 first. And now you have 2, and that's equal to this. Okay. Now the other thing is, even though there's 2 items in here, since there's parentheses, you know that this exponent belongs to both of these items. This whole entire briefcase is attached to that exponent. So you're still allowed to just go up and do this. Raise both sides of the equation to the 5/1. And what will happen is those exponents will cancel. This will be a crazy number, 2 to the 5th, which happens to be 32. And this just falls out. Now solve the equation like you normally would. So I'm looking to find b, so I'll add 19 to both sides. And I get 51 on the left. That's somehow equal to 3b. The last thing I should do is divide by 3. That will get b all by itself, which happens to be 17. Okay, question 20. We're talking about equations again. So remember, whatever you do to an equation on one side, you got to do to the other side. The last few questions talked about getting rid of exponents. And what we would do is raise both sides to the 4/3. Okay. Oops, sorry. In this case, we're talking about radicals. So how do you get rid of radicals? To get rid of a radical, you square it. Because a radical times a radical is whatever's underneath. For example, radical 3 times radical 3, if you wanted to be pure about it, you'd say, okay, you multiply what's underneath and you get the 9. But then when you simplify, you get 3. So it's no coincidence that when you multiply identical radicals together, whatever's underneath those radicals just falls out. So in other words, radical 3 squared is pretty cool. It's just 3. That's the property we're going to use here to solve this equation. We're going to raise both sides to a square. And then what happens, which is kind of cool, is this just goes away. And what you're left with is what's underneath. So you have this really nice, simple equation. Okay, so now let's solve for x. I'm going to add x to both sides. I always like to keep the x's positive if possible. So this is a nice, positive 4x. Let's add 13. 4x is 20. X is 5. Okay, listen. Radical equations, you got to check. It's that thing called extraneous roots. And it just means that, not every answer is going to work. And sometimes when you factor in these equations, and you know how when you factor, you normally get more than one solution, oftentimes that solution doesn't work. So let's just take a quick check. You have the time, you might as well. Is the square root of 3 times 5 minus 13, is that equal to the square root of 7 minus 5? So I look over here, it's the square root of 15 minus 13. Is that equal to the square root of 2? Well, without even figuring out what the square root of 2 is, I can see that that would definitely be equal, because the square root of 2 is certainly equal to the square root of 2. 22 is a question that I hope all of you watch. Just for this reason. Many of you probably realize that when you solve radical equations, it's quite simple. You just square both sides. And what happens is underneath the radical basically just falls right out. That's cool, because this just goes away. Now, this is what kills me. This thing squared is not v squared plus 16. It's not v squared minus 16. It's none of that. Please remember that when you square a binomial, or when you square anything, you're doing it twice. So if we can just take a second to see visually what we're talking about, if you square v minus 4, it's like saying v minus 4 times v minus 4. It's no different than squaring 3. It's not like we're changing the rules just because it's binomials. If you square 3, it's like saying 3 times 3, which is the obvious 9. So back to this. Squaring that is not v squared plus 16. It's pretty close. It's not like you're a mile away. But when you FOIL that, you're actually going to get, here we go. V squared minus 8v plus 16. Okay, because we FOILed. All right, so now it's pretty simple, except at the end, we really have to check because on all radical equations we need to check our solutions. I want to set this equal to 0 because I have a quadratic. So whenever you're trying to solve for quadratics, don't we usually set it equal to 0, factor, solve? So those will be our steps. Let me write those over here for you. Let's set this equal to 0. Let's factor, solve, and then check. These are really important. Okay, so setting equal to 0 looks like, let me take away v and take away 2 in one step, just to save some time here. Okay, so I'm going to take away v and take away 2 from this side. I'm left with v squared, negative 8v minus v is negative 9v. 16 minus 2, 14. Okay, we set equal to 0. Factor. Most of these work out pretty easily, but you do know all the methods of factoring. GCF, dots, difference of cubes, AM method, AC method, earmuffs. Use the quadratic formula to solve, whatever you need to do. But most of the time, these work out pretty nice. So you have v and v. What adds up to 9? Multiplies to 14. I think it's 7 and 2. It's got to add up negative, so it's going to be negative 7, negative 2. Okay, so we factored. Now we're going to solve. These usually are t-charts, right? Set both sides equal to 0. So this would be v equals 7. This would be v equals 2. And this is the most important thing. I mean, you can tell by the answer key already, right? But in case you don't have the answer key in front of you, you have to check. So let's look at what happens. Let's take a peek at the 7. Okay, v equals 7. And we'll do over here v equals 2. Kind of split it. Okay, for v equals 7, we're going to say in the original, 7 minus 4, are you equal to the square root of 7 plus 2? 3, are you equal to the square root of 9? Definitely. Cool. Okay, for v equals 2, so we have 2 minus 4. Are you equal to the square root of 2 minus 2? So this is negative 2. Are you equal to the square root of 0? No way. Okay, so what you do then is you say solution is, if you want to put it in set notation, 7. And you reject the 2. And if you want to be all fancy and get like brownie points, write the word reject over here, because your teachers or the graders will know exactly what you're talking about, which is very nice. Okay. (24) is an equation, no doubt. And you're solving an equation for this variable n. The only problem is, we've been solving equations like this up until now. We would have something like 2n equals 8. So we would just divide both sides by 2, and we'd get n equals 4. Then we had equations like this. N to the 2/5 equals 8. We would raise both sides to the 5/2. Make sure we do plus or minus because this denominator is even. So we would just say n equals plus or minus 8 to the 5/2. Then we had these things like this. Radical n equals 8. So what do we do to solve radical equations? We square both sides. That gets the n out of the radical, and we get n equals 64. Here's the problem with this question. The n is up in the exponent level. It's not just an expression, it's not a base, and it's not a base here. It's up north. So when the n is up in the exponent level and we haven't figured out logs yet, this is what we do. We look for something called a common base, because we know that if we can do something like this, let's say you had like 3 to the 2x, and that was somehow equal to 3 to the 4x minus 10. If this is a true statement, like an equation, well, 3 to the something equals 3 to the something. These somethings are obviously the same, otherwise this wouldn't be a true statement. So you can almost say forget the 3's, because I know these two things must be equal. Let me just set them equal to each other, and that will tell me what the value of x is. So it's the same for these guys, except the only difference is no one handed you a pair of 3's. 625 and 125 are not the same, so you can't just cross them out. And that's why this topic is called finding a common base. Let's find some 3's or 5's or 6's or whatever it is so we can get them the same. So that's what we're going to do here. Okay, so 625 and 125. It's not exactly the easiest one in the world, but I'm looking at 5 and thinking, I know that can turn into 125 because that could be 5 cubed. There's no science to this. You just have to, guess and check. So I just happen to know that 5 to the 4th would equal 625. So my common base for this question will be 5. So let's figure out what do we do with that information. So this is what you do. Let's take this 625 and let's call it 5 to the 4th. And bring this original exponent down. Now on the right, let's call this 125. Let's call that 5 to the 3rd. And bring the exponents down. Now use your power rule, which means to distribute, right? You're going to multiply. So I will simplify this to be 5 to the 4n minus 8. And this would be equal to 5 to the negative 3n minus 6. Well, check it out. These bases are the same, so you get rid of them. And you just set the tops equal to each other. And it really becomes a very simple question once you figure out the common basis. Okay, so set this equal to 0. I think I'll add 3n. Again, I always like those positive variables, right? So I've got 7n here, minus 8 equals negative 6. Let's add 8 to both sides. I've got 7n equal to 2. Dividing both sides by 7, final answer, n equals 2/7. Cool. Common basis. I wanted to do 25 with you because it's a common base question with a little twist. And I think these will be the types of questions you'll see on our Regents because it just takes it a little bit to the next level. So for example, 16 to the 3x equals 1 over 64. You know you want to use common bases in these questions because you're looking for a variable that's up in the exponential world. It's not just at the expression level. You're trying to solve for x, and x happens to be an exponent. So that's a little funky. So that's how you'll recognize common bases in this unit. But then you're thinking to yourself, how am I going to get it to be, like this? Really? One more time. How am I going to get it to be like this? How can I get the common bases and just solve for the top when this thing's a fraction? Kind of looks a little weird. This is what I'm going to tell you. Whenever you see fractions and you're thinking about common bases, forget the fractions for now. Just focus on the numbers. So 16 and 64, don't stress that that's a fraction of 64. Just think, okay, 16 can be 4 squared, and 64 can be 4 cubed. So your common base is going to be 4. So watch what you do. You take your 4 squared and raise it to the 3x power, because that was the original exponent. You can't forget that. And now when you get here and you want to use the same 4, just put a negative on it. Put a negative on that exponent, because after all, if you had 4 to the negative third, that would be the same as 1 over 4 to the positive third. And that's where your 64 ended up in the basement. So if you ever see fractions, don't stress them. Just find the common base and give the fraction a negative exponent. So I'm going to say here 4 negative 3. And we're going to raise that to the 1 that was there. Cool. So now the power rule comes into play, right? So 4 to the 6x, and that's equal to 4 to the negative 3. Cross out those bases, and you have 6x equals negative 3. Solving this equation, you get x equals negative 1/2. Okay, common bases with fractions, just make the exponent negative. 26, same as 25. If you see a fraction and you're working with common bases, just make the exponent negative, that's all. So watch. 9 squared, that could be my 81. And 9 to the negative 1 could be my 1 over 9. So in terms of common bases, I'm done. This is 9 squared. I'm going to raise you to the m. And this would be 9 to the negative 1. And I'm going to raise you to the 3m minus 2. Using the distributive property for the product rule, right, we're going to multiply. There you go. And then this guy is negative 3m positive 2. Look at these common bases. Gone. Simple equation now. 2m is equal to negative 3m plus 2. And just solve like you normally would. So I'm going to do this. I always like keeping mine positive. You don't have to, but I just like that. So 5m is 2, and m is 2/5. Not bad, right? If you see fractions, common base, just make the exponent negative, you're done. I wanted to go over this question, 27, just because if you look here, it's a common base question, right? It's an equation where you're looking for an exponent value, so you make them a common base and cross them out. But I wanted you to know that it's the same story even if you have 3 expressions. It's not a big deal. It just means you might have to do a little more work first. So in terms of the more work, what I'm saying is let's get common bases for all 3 of these. So 5, I'm going to turn that into 5 to the first. Really no change. I just want to show you the process. 125, I'm going to make that 5 to the third. And 25, I'll make 5 squared. So here's the little bit of extra work that I'm talking about. We're going to have to combine these. But you can't just combine these when they're different bases. But we can combine them if they're the same base using the power rule. The product rule. My bad. So watch what I mean. We'll take this guy to be 5 to the first, raising him to the second power. This one we were saying was 5 to the third, raising that to the 3r. And we called this one 5 squared, raising that to the negative 3r. So we're just going to combine these two is what I meant by the extra work. Because it's 5 squared times 5 to the 3r. If you use the product rule, the base stays the same and you add exponents. Now you set that equal to 5 to the negative 6r. Okay, so a couple more steps than we're used to with these common base questions. That's why I wanted to show it to you. But now we do have a common base, and we can simply solve for the tops equaling each other. So 2 plus 3r is negative 6r. I don't know. Let's add 6r to both sides. I'm really a stickler with this positive stuff, even if it means emptying out this side for a second. Okay, 2 plus 9r equals 0. Take away 2 from both sides. 9r equals negative 2. Divide by 9. Sorry for running out of room. R equals negative 9 halves. I'm honestly just checking the answer key right now to see if that's right. No, I messed something up. Did I mess something up or the answer key messed something up? Let me check. 5 squared. Oh. Whoops. This is 9r, people. Someone should have stopped me. This is 9r. Okay, so let me go back and fix this. Okay, so this is 5 squared times 5 to the 9r, and that's going to be equal to 5 to the negative 6r. So we can combine these to be 5 to the 2 plus 9r. That's just using the product rule. And that will be set equal to 5 to the negative 6r. And after we did those extra steps, look what happened. We finally got our common bases, we cross them out, and we solve this equation. So the equation is 2 plus 9r equals negative 6r. That's all. So I'm a stickler for this positive stuff sometimes to my demise, but I'm going to add the 6r to both sides. So now I get 2 plus 15r equals 0. I'm going to send the number to the other side. So 15r is negative 2. Dividing by 15, r equals negative 2/15. Number 29 is a graphing question. And the best thing to do here for double checking or getting some difficult numbers is to use your calculator. So please be aware that you can just put this in your calculator as y equals. And this will show you what you're looking at. But there are some topics that you need to know about graphs of exponential functions. And those would be things like the domain and the range and the asymptotes especially. And then of course end behavior. So something for you to know that was in your notes for some of these previous videos on exponent graphs was the fact that if you have a function like this, the asymptote is always x equals 0. I'm sorry, y equals 0. Because the graph would look like this. And you can use your calculator to verify that. So this is something very important to know. Another really important thing is this y-intercept. This always occurs at 0, 1. for an exponential function. Something else to recognize. If this number is greater than 1, right? 6 is definitely greater than 1, then you're looking at something called growth. Whereas if this number was less than 1, then you'd be looking at decay. For example, what if we had f of x equals 0.7 to the x? I tell you what, it's going to have an asymptote at y equals 0. It's going to pass through the point 0, 1. However, it will be declining as you move across the x-axis to the right. So we still have this nice 0, 1 point. We still have an asymptote, which is basically a limit. It's where our function is trying to get to but just can't. It gets very close but never touches. So that would be called y equals 0. Now, things that affect these points, these asymptotes, and these y-intercepts are the shenanigans located right over here. It's when we start shifting and moving a regular exponential graph. So on this particular question, we're taking a parent function. Let me clear this all out, sorry. We're taking this parent function, which has all the properties that I just described, looking like this. It has a y equals 0 asymptote. It has a y-intercept of 0, 1, all that stuff. But it's shifting it to the left 1 unit and shifting it up 1 unit. So for example, let's graph the parent function, 2 to the x. I know it goes through here, and I know it has an asymptote at the x-axis, aka y equals 0. Let's draw this graph. I'm not going to be very good at it, I'll tell you that much. So I'm just freehanding it here. But that could be my parent function. Now, if you wanted to be more accurate with graphing, you can go to your table of values in the calculator, and for example, you would see this. 0, 1, 2, 4, 3, 8. You know, so I should be somewhere over here at 2, 4. I should be somewhere over here at 3, 8. So I kind of had it. You know, I literally just sketched it. But that can help you to graph a little better. Grab your table of values. Now let's talk about these shifts. So what's happening here is when you have a number in this area, you are just shifting to the right or left in the opposite direction of the sign. So if it says -1, I'm going to take this graph and move it to the right 1. Then if it says +1 over there on the outside of my function, I'm moving it up 1. Now that has some pretty dramatic effects on a couple of things. The asymptote, for example, it's no longer the x-axis. It's now, if you imagine a plane landing, it's landing on a runway that's located at y equals 1. And notice the y-intercept. Funny, it kind of looks like it still goes through the same. I don't know, maybe it does. But, you know, you can imagine that the y-intercept would change depending on where this guy goes, you know. Okay. So, how do you know a y-intercept? You plug in x equals 0. So, if I really want to know my y-intercept, I would do this. And I would get 2 to the 0 minus 1 plus 1. And if I'm not mistaken, that's 1.5. Okay, so that looks pretty close. It's a little higher than 1. Okay, so now the asymptote is going to be y equals 1. The domain and the range. Okay, well the domain is going to be all real numbers because this graph is unrestricted. It goes all the way to the left, and even though it's aggressively heading northbound, the general tendency of this graph is to be heading northeast. I could put any value of x I wanted into this function. It would just be a gigantic number. So the domain is all reals. Now range is the y-axis, right? So the range is going to be, oh, positive infinity, because there's the arrow heading northbound. However, remember the asymptotes. This graph comes down and lands, or tries to land, on the line y equals 1. Therefore, it never goes below it. So the range is pretty much restricted to be y greater than 1. Not equal to, please, only greater than, and less than positive infinity. End behavior. That's just a fancy way to say what happens as the x's go to the right and what happens when the x's go to the left. So, no magic. Let's just talk about it. So as x, and then you draw this line which means approaches, positive infinity, what's happening to the y values? What do they approach, or what do they do? So as x goes to the right, I'm looking at a graph that's heading to infinity. So I write that. Now let's go the other way. As x heads to the left, which is just a street way to say as x approaches negative infinity, what is my graph doing? It's landing, or trying to land, on y equals 1. Never gets there, but it's getting close. So what we'll say is y approaches 1. And that's the topic. Use your calculator for sure. It can help you with the asymptotes, and it can give you an idea of, domain and range and things like that. Okay. I like question 30 because it shows a decreasing function. We said that if this parent function had a value less than 1, it would be decreasing. So I just wanted you to take a look at this. It's very, very much like the previous question. The only difference is it decreases. Like this. And the parent function of this exponential is this. F of x equals 0.5 to the x. So 0.5 is definitely less than 1, and that's why we call this a decay. Because as you move from right to left, left to right, the graph is shrinking. So now let's talk about asymptotes. Thanks to this guy right here, the asymptote will be y equals 2. The domain is going to be all real numbers because you can see that there's no restrictions. This graph goes to the right forever. You couldn't imagine any number that couldn't go here, right? It's just a very straightforward function. You're just plugging in a number for x. There's no variables in the denominator. If that were the case, you couldn't let x equal 0, This is completely unrestricted for the domain. The range, however, when you talk about exponential functions, has everything to do with the asymptotes. So this graph goes to infinity for the y values up top, but only lands on this asymptote and never actually gets there. It's like a magnetic field, the number 2, and it says you can get close, but you'll never be able to touch. So the range will be from 2, soft bracket, because you're not equal to, and stopping, if you could possibly stop, at infinity, soft bracket. Cool. Another way to write that, y greater than 2, less than infinity. Nice. Figuring out if functions are increasing or decreasing is as simple as using your graphing calculator. However, the theory behind it, in case you were asked to explain or justify, why is this a decreasing or an increasing function, besides just saying because my calculator said so, is this business right here. If that's greater than 1, you are increasing, generally speaking. If the value attached to the exponent is less than 1, you are generally decreasing. However, look at 34. The value attached to the exponent is greater than 1, so I'm going to say temporarily you're an increasing graph. But that wouldn't be correct because of this crazy-eyed killer right here. It's negative. -2. So when you have negative exponents, it flips the rules around. So when you have a number bigger than 1, but you throw in a negative exponent, this graph decreases. So imagine this right here. I'm going to think it's decreasing. But whoops, being that that guy's negative, it reverses the effects of the graph and turns it into increasing. Now, this is all verified through your calculator, so there should be no reason you'd get this question wrong. But I just wanted to show you why. These negative exponents reverse the effects of the graph. Because after all, let's just focus on this for 1 second over here. Forget the t. If you had 2 to the -2, that's the same as 1 over 2 to the +2. So that number, if you started to increase it, 1 over 2 to the 3, 1 over 2 to the 4, right? You start getting that exponent larger. You increase the x values. It's funny, when you're a fraction, you're actually getting smaller. If I had half a pizza, that'd be certainly a lot more than 1/8 of a pizza, which is much more than 1/16 of a pizza. So that idea of a negative exponent putting you into the denominator as a positive exponent, when your denominator gets larger in value, the value of your fraction actually decreases. And it's the same thing here. When you're a fraction with a negative exponent, for example, 1/2 to the -2, that would be like saying 1 over 1/2 to the +2. So what is that? Well, that's 1 over 1/4. And then if you made the 2 a 3, it would be 1 over 1/8 and 1 over 1/16. And you're thinking, well, isn't that the same story as the last thing you just said, where the bigger the denominators, the smaller it is? That's true, but this is a fraction of fractions. So when you divide 1 divided by 1/4, you would agree that you do a keep change flip and bring that 4 over 1 up top. And that would give you 4. Same thing with the 1/8. If you divide 1 divided by 1/8, keep change flip, that turns into an 8. So as you can see, the numbers are getting larger as the exponents are increasing. So even though I was less than 1, and that's a decreasing function, this negative exponent reversed the effects. Cool. 37, let's start working on some of these word problems with exponential growth and decay and compounding periods, all that stuff. What I want to point out right away is this. If you see continuously, you're talking about E. E is the second divide key on your calculator. That's how you'll get E. The formula you use for this is APERT. The amount you have at the end is going to be equal to the amount you started with times E raised to the power of rate times time. So Ariana has a choice of 2 investments. They're both compounded continuously. She can put 12 grand in at a rate of 5%, which is 0.05 for 8 years. Or she can put 9 grand in different percentage rate, 6.5%. So that's 0.65 for 7 years. The question is, which investment will result in more cash? Nope, I take that back. More interest. So this isn't a race to see who's got the biggest pile of money. This is to see the difference between the amount invested and the amount returned. That would be called your interest, or the money you made on top of your money that you already had. Cool. Okay, so let's find out. What are the amounts we end up with? So, just by looking at the answer key, because I don't have a calculator in front of me right now, I see that this amount was 17,901. This amount turned out to be 14,185 and 56 cents. Oh, and this guy had 90, sorry. Okay, so I think the 17,000 guy wins, but maybe not, because it's not a question of who's got more cash. Who earned more interest? Was it a 6.5% interest rate? Was it a 5% interest rate? You know? Well, how do you know what the interest is? Well, what we said was it's the difference from the amount you started with to the amount you finished with. So we'll take away the 12,000 here, and we'll get an answer of $5,901.90. When we check out the 14,000, we had started with $9,000. So the interest that we earned was $5,185.56. Okay, well, in this case it was that guy, but only because the question specifically said, who made more money? Question 38, starting with 25 members, a club doubled its membership every year. Okay. Doubling in terms of a percentage of interest or a rate of growth is 100%. And when you move the decimal twice to the left, you get 1.0. So that's going to be our rate. Just like half-life questions are 0.5, okay? Think of it that way. So doubling your money is like getting 100%, 1.0. What kind of formula are we going to use? We've got 25 members, so I'm thinking P is 25, because that's the amount you start with. A is probably who knows how much, don't know. The rate is going to be 1.0. Is there any kind of compounding going on? The club doubles its membership every year. Write the function that expresses the number of members in the club after some amount of years that they're calling N. Usually we use T, right? So they're using N, no big deal. Then find the number of members after 6 years. Okay, so there's no compounding. It doesn't say continuous. It's just a very simple annual formula, which looks like this. Amount equals the amount you started with times 1 plus the rate raised to the, we'll say, N years instead of T. Okay, so I think we're good. We can make a formula. They gave us enough to plug this in. 1 plus 1. That's funny. Raised to the N. So if we simplify just a little bit, just to make it look nice, that's our guy right there. Okay, so that's question number 1. Part 2 said, using that, what would you get in 6 years? So let's put that right there. So part 2, amount equals 25 times 2 raised up to the 6th power. That turns out to be a whopping 1600. Very cool. Half-life. Now that formula, just like the one we just did where it was doubling, half-life is just pretty cool. It's the amount you started with, spoiler alert, times a half, right? Because you're halving it. And then you just have to raise it to how many years you've been waiting around over how long it takes to make a half-life. So oftentimes it's a fraction. So what is this thing saying? A half-life of radioactive is the average amount of time it takes for half of the atoms to decay. Suppose you started with 500 grams. I gotcha. With a half-life of 10 minutes. Okay, so scratch the years business. We're converting this into minutes. So that would be 10. Ooh. No, it wouldn't. 10's on the bottom. Sorry about that. Because they're telling us the half-life is 10 minutes. Okay, so for every 10 minutes this thing will trigger. It'll cut itself in half. How long are we going to do that for? How many grams to the nearest tenth are left after 10 minutes? Ooh, so this first guy's kind of cool. Very easy, right? Because 10 minutes over 10 minutes is really just to the 1, which is cool. So the answer here is going to be basically half of 500, you know? It's never usually that easy, so don't get crazy. It might get a little weirder. You're going to have to use your calculator. But for this guy, it's 250. Nice. Okay, question B. Question B, how many grams to the nearest tenth are left after an hour? That's tricky. They're saying hour, we're talking minutes. So there needs to be a conversion so that when you make your fraction, you have the same units, right? So 500 times 1/2 raised to the 60 minutes that we've been sitting around waiting, over every 10 minutes it'll half itself. So unless you live in West Virginia, you know that that just means 6, right? So it's actually a very nice, easy problem. You're just going to go to your calculator and say 500 times 1/2 raised to the 6th, and we're going to get rounded to the nearest tenth, 7.8. Question BB, or we'll call that C. Question C. How many grams after 33 minutes? Now this is more realistic. I like that because you're getting a crazy fraction. So it's 500 times 1/2. We've been sitting around for 33 minutes waiting, and every 10, it's going to cut itself in half. So that's a dicey sort of situation because 33 does not get divided by 10 evenly. So this is when your calculator is a must. And when you round it to the nearest tenth, we end up with 50 over 8. I'm sorry, 0.8. Nice. Cool. Okay, so question 40 is talking about the growth of some northern sea otters. And they're telling us it's annual growth of 18%. So when you're dealing with annual growth and somebody doesn't use the word continuously, you have to assume the very basic annual growth formula. Even though you might be tempted, as I am right now, to use E, because we're talking about nature, unless it says continuously, resist the urge and just go with what you know. They're telling us it's annual growth. We never hear the word continuously. Therefore, we're going to go with that nice formula that looks like this. The amount you have left over is the amount you started with times 1 plus your rate raised to how long you've been waiting. Let's plug in what we know. 70 were the starting number. The rate was 18%, which is 0.18. Move the decimal twice. How long is T? How many you have is A. That's the answer to part 1. Now, how many will there be after 4 years? So common sense says it better be bigger than 70, right? You should think that way when you do these problems, just so you don't get suckered into a wrong answer. We're talking about population growing, not decaying. So make sure your answer is somewhere around 80 or something. Let's see, 70 times 1.18 raised to the 4, and the amount of sea otters that you'll have is 136. Whoa, I was way off. But at least it's bigger. That was what was most important. So the answer here says 136. For the time being, the way I will grade your tests is if you have 135.7 sea otters, I'm assuming there is no such thing as a 70% of a sea otter. I would just assume that one of the sea otter mamas is pregnant. So let's agree that we're going to say 135 sea otters, because 136 is sort of not exactly there yet. So when you talk about population growth of people or animals, you need to just count the wholes, the whole parts, okay? So although in mathematics we would generally round 135.7 up to 136, for sure, you know, when we're talking about population, let's just count the whole amounts. Either way on the test will be okay. I promise you that, but I would much prefer to see you write this, because I believe that that's more accurate. Okay, I've said too much. So we're up to 42. Nice. Ernie invested 500 bucks at a bank. He's got 4% monthly. How much will he have after 5 years? So when you're compounding, you use this formula. The amount equals the amount you started with times 1 plus the rate, except now you divide by the compounding periods and you also multiply by the compounding periods. So we introduce this new n when you have some sort of compounding. So what's our compounding? Monthly. So 12. There's 12 months in a year. So let's see what we get. The amount Ernie will have is equal to the amount he started with, which was 500. He's earning money, so his interest rate is positive, so it's plus 0.04. If he was paying back a loan, it would be negative 0.04, right? How much will he have after 5 years? So that's going to be 12 over here, 12 over here, and then 5 for time. So when you do this in your calculator, you end up with $610.50. The most important concept here was the compounding monthly, which forced us to do a 12 here and a 12 here. This is a blast from the past, but it's very important that we keep remembering this topic and all the other ones that, back from when the Earth cooled and we first met in September, because this will all be on the regions. When you have points x and y, and you plotted these points on a graph somewhere, who knows where they'll be? And if you tried to connect them, it might look pretty crazy. But believe it or not, when we are given x's and y's, we are able to determine where they possibly came from. Like maybe this represents something like this. And it would be a parabola, right? And if you went to your table of values, you would see these x's and y's. Perhaps it looks like this. I mean, any combination. Even something ridiculous like that, 4x cubed minus 4x squared, and so forth. You go to your table of values, those would be the numbers. And so on, and so on, and so on. So in this course, we've learned that given points, x and y, we're able to determine what the degree is of the polynomial that was responsible for them, like the ones I just drew randomly. And the way we can find that out is by this thing called successive differences, which are really just brilliant how it works out. The only thing to remember is to go bottom up. Bottom up, subtracting, and make sure your x's are in order. Or what would you say, sorted? So what do I mean by that? I've never seen it not that way, but just in case, these x values, 3, -2, -1, 0, 1, 2, 3, have to be sorted so that you're starting with the bigger numbers first. So the bigger x's is your starting point. The bigger x starts. And then we just work our way up, subtracting the y values. And check this out. It's like really, really cool. Let's see what the differences are for our y values, bottom to top. So 24 minus 8, that's 16. 8 minus 4, 4 minus 6, 6 minus 8, 8 minus 4, 4, subtract -12. Okay, are these numbers the same? No. So it's not an x to the first. It's not a line, is what we're saying here. So then what you need to do is subtract again. These guys. Let's see what we get. Bottom to the top. 16 minus 4, 4 minus -2, -2 subtract -2, -2 subtract 4, and 4 subtract 16. Not the same. So it's not an x squared. It's not a second degree polynomial. You got to keep going. Third difference. Bottom up, 12 minus 6, 6 minus 0, 0 minus -6, -6 minus -12. Bam. Check it out. They're all the same. That means it's a cubic. I don't know what kind of cubic it is. It's kind of wacky. It could be any cubic, but it's definitely cubic. So what do you know about those? Well, if you're an odd degree, you've got n behavior, that looks like that, or that. How do you know which one's which? Well, if the leading coefficient is positive, it's that guy. Negative, it's that guy. I hope this is coming back to you. Now, if you're an even degree, which this is not, but we might as well talk about it, if it turned out to be the second or the fourth difference, right, that would be an even degree. Your end behavior is either like this or like this. Again, how do you know? If the leading coefficient is positive, it looks like two guys going up. Negative, two lines going down. Oops. Somebody stop me. There we go. Negative. Sorry. Okay. So knowing the end behavior is a matter of knowing your leading coefficient. So in this answer, my leading coefficient is positive because my difference was positive. That's all. Because this guy was positive. I've seen them negative, so it happens. It's going to be one or the other. Nothing very special there. It's very random. So you have to know both for sure just to be safe. Okay, so what's this question saying? Determine the degree. Okay, the degree is 3. That's the first answer. What's the end behavior? Well, it's an odd one. My guy was positive, so it's this. What kind of end behavior is that on a graph? Well, if you can picture that on a graph, what are you looking at? You're looking at this, and then that. So as x approaches infinity, which means I'm going to the right, my y values are heading northbound, which is infinity. Now when I'm going left, which is just a street way to say approaching negative infinity, my y values are heading south forever. And that's the end behavior. Pretty cool. Just remember a couple things, okay? Bottom up. My apologies to, I believe it was third period that I went top down. I'm very sorry. And make sure your x's are in order. Start with the bigger x. And whenever you get the matches, that's your degree. 47 and 48. Long division for number 47. Okay, long division. Make sure you're not missing anybody. So, just for some notes, place exponents in order. Replace any missing ones. And you'll replace them with zeros. Is that how you spell zeros with an E? It just looks right, I guess. Okay. And that's it. So are these in order? Yes. 3, 2, 1, nothing. Perfect. So we're going to take this x plus 3, and we're just going to do long division like we did in elementary school. There's really nothing fancy here. Just a couple of things to remember which will help you tremendously. Like, for example, how do you start this? Well, the thing is, just look at the first term. Don't worry about the second one. And just look at the first term here. Don't worry about anything else. It'll all just work itself out if you just look at the first terms. You're asking yourself, how do you get from x to x cubed? I think you'd agree that you would multiply by x squared. So now what you do is you have to distribute to these two terms and write your answer below as a subtraction. So this should always match up because after all, you're the one who did it. You were looking at the first terms, right? So the first term better be what you were looking for, x cubed, so that it disappears when you subtract. The second term will always be random, right? So x squared times positive 3 is positive 3x squared. What happens next is you subtract, These go away as expected, and you get negative 2 subtract positive 3. That's going to be negative 5. If there's any terms left, bring them down one at a time. And again, ask yourself, how do you go from the first term, x, to the first term, negative 5x squared? What would you multiply by? In this case, I would multiply by negative 5x. So I put that term up here. And then I go about with my distributions. I write the answer down here as a subtraction. I use parentheses just as good habit. And of course, the first term has got to be negative 5x squared, because we want them to cancel. The second term is going to be negative 15x. When we subtract, these go away. Here's why I like to use parentheses, not just wasting your time. Look at what happens. You have negative 8, subtract negative 15. There's a double negative there. It's very easy for me to see because I'm using parentheses. So negative 8 plus 15 is actually a positive 7x. I still have this term, so I'll bring it down, and that's a positive 21. Again, looking at the first terms only, how would you go from x to 7x? I think you'd say you'd multiply by a positive 7. When you distribute, you get 7x positive and positive 21. Notice what happens when I subtract these. Everything goes away, and there's a remainder of 0. When your remainder is 0, you have identified a factor. And that's what the game is here. So when the remainder equals 0, you have a factor. So the answer to this question is yes. And the way we proved it was we divided the alleged factor into this polynomial, and we ended up with 0. Perfect. Okay, 48. This is the old parabola with the vertex situation and the directrix and all that, right? So we need to know our equation, which would look like this. X minus h squared equals 4 times p times y minus k. H and k is the vertex, but switch the signs. P is the distance from the directrix to the vertex, or it's the distance from the focus to the vertex, or it can even be the half the distance from the focus to the directrix. Okay? So a couple of things to remember. If you have a directrix over here and a focus over here, parabolas always open up away from the directrix. They're scared of the directrix, so they're running away in the opposite direction, sorry. And the focus is always inside the parabola, like it's a salad bowl holding onto the focus. Or it's a satellite dish, and the focus is the arm that collects all the signals, which is actually the case. So a vertex is always the tip of a parabola, whether it's on the top, or maybe it's a parabola that opens upward and it'll be on the bottom. But regardless, the vertex is at the very tip of a parabola. focus is always inside the parabola, and the parabola always opens up in the opposite direction of the directrix. It runs away from it. So how are we going to figure any of this stuff out? Well, let's start with the vertex. The vertex is going to be +2, -1. So +2, -1. That's the vertex. Now, which way is my parabola opening up? I mean, opening. Is it opening up or is it opening down? That depends on the directrix. I don't exactly know where my directrix is. Okay. Well, here's something else to know then. So if P is negative, the parabola opens down. So if you don't know where your directrix is, you can just look at the p-value, and if it's a negative p, you'll know that the parabola has to open down. So let's just write that down for your notes. If p is negative, parabola opens down. Cool. So, I don't know exactly where it is yet, but I'm just going to assume, that's my parabola, and there better be a focus somewhere in there like that. All right, so let's go figure that out. There's my vertex. Okay, so what's the distance from my focus to the vertex? Or maybe even my directrix to the vertex? I need to know my p. So if I look at this formula, it says 4p goes right here, right? If I look at the given equation, my 4p was set equal to -10. Well, then I can find out what p is. Divide both sides by 4, and p is equal to -5 halves, or 2.5. So how does that help us? -2.5, sorry. How does that help us? Well, I know that the distance from this vertex right here to my focus is going to be 2.5 units. So 1, 2.5. So that is going to be my focus. Cool. 1, 2.5. Very cool. Therefore, I know my directrix is going to be 1, 2.5 above, because I have a downward opening parabola. That means my directrix is on top. And you know that the focus, like a salad bowl, it's always inside of it. So I'm just going to sketch this hideously right now. I'm sorry. But it's something like this. Not bad. This distance is called your p. And it's the same on both sides. It's 2.5, negative. So last part is this. The question says leave it as a fraction. So we're going to go with that. And there you go. Good luck on your test.